Alright, so this is LeetCode 104, maximum depth of binary tree. So given the root of a binary tree, return its maximum depth, and a binary tree's maximum depth is the number of nodes along the longest path from the root node down to the farthest leaf node. Okay, so in this example, right, it's the number of nodes, let's highlight that, along the longest path from the root node down to the farthest leaf node. So in this example, this would be this path down here would be 2. These are considered leaf nodes. This 9, 15, and 7. These nodes right here are considered leaf nodes because if you imagine this being an actual tree, these are like the branches, and then the nodes at the very end with no nodes beneath them, like no children nodes, are branches, or are leaf nodes actually, sorry about that. So these are leaf nodes. Right, so this path down here would be 2. This path would be 3. And then this path would be 3 as well. So out of all these paths, what would be the maximum depth? We have 2, 3, and 3. 3 and 3 are equal, so we just return 3, right? Okay. So that's kind of the explanation of this, but how could we actually solve this in code? So this question is kind of leading you towards using one of the tree traversal algorithms, which is called not breadth first search. I think you might be able to solve this using breadth first search, but I'm thinking of depth first search, or DFS. So DFS would go along this path, and it would go as deep as possible, and basically go along the paths or branches. So what we could do is we're gonna call DFS using recursion, right? So what we're gonna do is we're gonna say what's the maximum depth of this node right here. This is 1. What's the maximum depth of and then we're going to go as deep as possible. We're not going to do it with this node. We're going to go, what's the maximum depth of this node? This is 1. Maximum depth of this node. This is 1. And then any node that it is a parent node, so this is a parent node, we're going to just basically take the maximum of its left and right child. So in this instance, this would be 2, right? Because it's the maximum of 1 and 1, which is just 1, right? This is the maximum of this would be 1, including this node would be 2, because, right, we're counting the number of nodes. Okay, so along this branch we have 2, and along this branch we have 1. Now this node is the parent node, so we're going as deep as possible, and then we're going to bubble back up. And then so we're going to do the maximum of the left and the right node, the left and the right subtree, and then this would give us, what's the maximum of 2 and 1? Well, that's 2, so we would favor this side of the tree, and so it would be 2 plus 1, which would give us 3, which gives us our output value. Okay, so let's see if we can write this in code and then maybe make more sense of it. Let's see. I don't think I looked at the constraints. So yeah, it says the number of nodes in the tree can range from 0 to 10 to the 4th. So meaning we could have 0 nodes, so we need to account for that. So if root is equal to none, or basically if it's equal to null, I'm going to put this in a comment. It's basically Python's version of null, I believe. We're just going to return 0, okay? Otherwise, we're going to return, we're going to count our root node because we want to have that in our value, right? Because if we just did the maximum of the right subtree right here and we take 2, it would be off by 1. So we want to do 1. This accounts for the root node. Plus, we're going to do self.max depth of the root.left, and then self.max depth of root.right. Okay, and then we're going to do the maximum of this. I think it's just, yeah. So what this function does, maximum does, say we had, say we gave this function 2 and 9, well, maximum would output 9, right? So you just give it 2 integers and it outputs the bigger integer. Yeah, so, sorry, I have the hiccups. Okay, so, yeah, so that's as simple as that. This is kind of the solution. To visualize what's really happening, basically we're calling the function within the function, but in this instance, we're calling maximum depth with this left subtree. So this function is going to get called again just with this left subtree, and then it's going to calculate that 1, and then once we finish, it's going to bubble back up and do 1 plus 1, which is 2, and then we do the maximum of the right subtree. I think it's honestly a little confusing to try to explain this recursion, but I think if I bring this into Python Tutor and walk through this, it might make more sense. So let me go ahead and pause this really quick. Alright, so I tried putting it in Python Tutor, but honestly it doesn't really visualize it nicely, so I think I'm just going to try to explain it one more time. And if you got it during the first explanation, feel free to just skip a couple minutes ahead where I explain the time and space complexity. But basically, again, this recursive solution, basically what we're doing is we're performing we're performing the maximum of the left and right subtrees on every subtree, right? So here we're going to do, and it's 1 plus that maximum, right? So 1 plus that maximum. So 1 plus this guy right here, 1 plus whatever this becomes right here. So if we go down here, how many nodes are on our left subtree? This happens to be 1. Okay. Now let's go down here. How many nodes is on our left subtree? 1. How many nodes is on our right subtree? 1. Okay, what's the maximum of left and right? 1 and 1. That just happens to be 1. So we would get 1 plus 1, right? Which would be 2. Okay, now what happens now? We get the maximum of the left and right, which is 1 and 2. That happens to just be 2. So we get 2 plus 1, which gives us 3. So that's kind of how the recursion works. It just basically calls the function multiple times, and by doing it on the left side, we're going depth first search on the left leaves first. Okay, so let's go ahead and try to find out the time and space complexity. Time complexity, let's see. This is a little interesting. I want to say that no matter what, this algorithm we're always gonna loop through every single node in the tree, right? So no matter what, we're touching every node, right? So I think that time complexity would mean that um, it's either, let's say that the number of nodes is n, then the time complexity would be n of n, or it might be um, the height of the tree. It might be O of the height of the tree. So say this is like 3. I'm leaning more towards this because I think because we have to touch every node means that that would be the time complexity. So as we gain more nodes, our amount of time that we need to perform this calculation is gonna go up. So yeah, I think this is the time. Okay, so space complexity, what is that? Space complexity. Initially, it doesn't seem like we're using any extra space, right? We're just calling the function. However, if I recall right, I think recursion uses a thing called a call stack. You can search up a little bit more about that, but basically, because of the call stack, when we perform recursion, we store a stack of, I think, the function calls, and that stack can get up to the height of the tree. So let's say that the height of this tree is, let's say it's of 3, I believe. I think this would be of 3, if I'm recalling how to do the height of a tree right. So if this height was 3, I'm going to put h here. If this height was 3, then our stack can be of length 3, basically. So our space would be O of h, where h is the height of our tree. And realistically, you can use any variables for these, but typically it's like n and h. H is just for height. Yeah, so that's what I believe the time and space complexity is. And yeah, thank you for watching.